Okay, so question 11 is about a structural member that is required to support the load given here. It's 250 millimeters long and no other geometric data is given, and it must not experience any plastic strain, so our stress levels must be below the yield strength. Using the given data below, select the material meets the criteria at minimum weight. So in this question we need to optimize the weight. So we start with this expression, sigma equals P over A, where A is the initial cross-sectional area. Now, as you all know, rho is density m over v, and for any prismatic member, whether it be a square or rectangular cross-section or cylindrical, this v, the volume, is cross-sectional area times the length. So if we leave this m alone, we have rho over rho times v, and this is equal to rho times A times L. From here, A is P over sigma, and M is equal to, then if we replace this, rho times P over sigma times L. If we rearrange these terms, we get rho over sigma times P times L. So in order to minimize the weight, you either have to minimize P, L, but these are constants. So our optimization parameter in this case will be rho over sigma, where sigma is our design strength, in this case the yield strength. So if we turn back to the table that is provided to us, we have the yield strength parameters here, tensile strength here, elastic modulus, and density. So for each material we need to compute this rho over sigma. We call in material science we call this a material specific index. So let us compute these for each given material. We have brass, steel, and aluminum alloy. Now in this index, the unit will not be important. All we want is that we require this to be minimum. Okay, so for brass, if we turn back to the problem statements, the table, we have 8.5 as density and 415 for yield strength. Similarly for steel, 7.9 over 320, and for aluminum, 2.7 divided by 275. If you compute these terms, for brass you will get 0.0205, for steel you will get 0.0247, and for aluminum you will get 0.0098. These are approximate, of course, not exact. So if we look at these values, we see that steel is the worst candidate for minimum weight and aluminum alloy is the best. So we must select aluminum alloy for the minimum weight criteria. So for question 12, part B, which material would you select for an application for which the resilient material is the primary requirement? We need to find the highest resilience. Again, the resilience expression is modulus of resilience sigma y squared over 2e. We have the yield strength values here, elastic modulus values here, and we compute them for each material: brass, steel, and aluminum. So if you compute the modulus of resilience for each material, the unit is megapascal in this case. I won't convert them to joules per meter cube, since we only need to compare and select. So highest resilience belongs to brass. So for highest resilience application, we must select the brass as our material.